Hey everyone. So in this video, I'd like to talk about simplifying trigonometric expressions. So later in the class, we're going to want to feel comfortable manipulating expressions involving trigonometric functions so that we can prove different relationships between these functions. And so I figured we can get started with this now and have a little bit of practice now that we've defined the 6 different trigonometric functions. And so I like to start off by saying that sometimes trigonometric expressions appear more complicated than they need to be, right? They're all defined in terms of sine and cosine, and so maybe there's some cancellation that can happen. So for example, if I take the expression tangent of theta times cosecant of theta, notice that, well, tangent of theta, right, this is the same thing as, this can be rewritten as sine of theta divided by cosine of theta. That's really one definition for what tangent of theta is. And cosecant of theta, well, that's the reciprocal function for the sine function, right? So this is the same as 1 over sine of theta. And so, we can simplify this expression by noticing that, these two consist of fractions involving sine and cosine, and when we multiply the numerators together, in this fraction multiplication, and when we multiply the denominators together, well, there's a common factor of sine between the numerator and the denominator to cancel out. And this leaves us with 1 over cosine of theta, which is the same as, well, this is the reciprocal of cosine, so I can think of this as the reciprocal trigonometric function secant of theta. And so all this to say that we can re-express this statement, tangent of theta cosecant of theta, as secant of theta, maybe a little bit more concisely. Okay, so this is an example of simplifying this trigonometric expression. And this word simplifies, it's quite open-ended, right? There's many ways you can imagine trying to simplify a trigonometric expression, but I hope you agree with me that this result we've ended up with is pretty clearly a simpler version of the original expression. So let's take a look at a different example. Let's go ahead and try and simplify this expression, the sum of these two fractions. And so if you're willing to try this example out yourself first, please go ahead, but we'll get started in just a moment. So here, we have two fractions here. I can imagine trying to add these fractions and seeing if there's going to be any common factor between the numerator and the denominator so that this fraction would reduce. And so let's go ahead and try that. So for us to add these two fractions, right, we need that common denominator. And so they'll need the new denominator of our resulting fraction. We'll need a factor of cosine of theta and a factor of 1 plus sine of theta. So here, this first fraction, I want to have the common denominator of cosine of theta times 1 plus sine of theta. It'll need an extra factor of 1 plus sine of theta. So I can multiply that to the numerator and the denominator of this first fraction. Right, that's not going to change that fraction at all, really. That's just multiplying by 1 in a very fancy way. And then I can take this second fraction, and right, I want that common denominator of 1 plus sine of theta as a group multiplied with cosine of theta. So I'm going to multiply this second fraction by cosine of theta divided by cosine of theta, right? Again, that's 1. And so there's no harm in doing that. It's not going to change my expression really, just really how it looks. And so here, if I multiply these first two fractions, right, this means multiply this numerator with this numerator. And maybe I'll do that off to the side here, actually, just as a little separate note. So 1 plus sine of theta multiplied with 1 plus sine of theta, right? This is kind of like polynomial multiplication, where I multiply every term in the first polynomial, or every term in the first group, with every term in the second group, right? So I get 1 plus sine of theta plus sine of theta plus sine of theta times sine of theta, right? That's squaring this sine of theta, and we usually express that as sine squared of theta, right? This means compute sine of theta and then square that result. And so this comes out to be 1 plus 2 sine of theta plus sine squared of theta. So that's the numerator of this first multiplication here, right? That's 1 plus 2 sine of theta plus sine squared of theta. And then my denominator, I'm just going to leave it factored as 1 plus sine of theta, right? This multiplied with the other denominator, cosine of theta. Okay, and then what about this second fraction? Well, we've got cosine of theta times cosine of theta, so that's cosine squared of theta, divided by 1 plus sine of theta multiplied with cosine of theta. And so the whole point of doing this was so that we would have a common denominator here, and that we could actually add these two fractions together. In other words, adding their numerators together. So here we get 1 plus 2 sine of theta plus sine squared of theta plus cosine squared of theta, all divided by 1 plus sine of theta times cosine of theta. And so, looking at this, we're tasked with simplifying this original expression, and it doesn't look simpler. It feels actually the opposite. It looks so much more complex than what we started with. But we actually have a useful tool here. So in the past, we made note of this identity that sine squared of theta plus cosine squared of theta, this always equals 1, regardless of that angle theta, just as long as it's the same between these two squared trig functions. As long as that input is the same between the two, the result is always going to be 1. This is the Pythagorean identity. And so here, I notice that I've got this sine squared of theta plus cosine squared of theta here, this relationship that these two, the sum of these two equals 1, actually helps us out quite a bit in this expression. We have 1 plus 2 sine of theta plus 1. That quantity always equals 1. And so from here, right, we've got 1 plus 2 sine of theta plus 1. That's 2 plus 2 sine of theta over 1 plus sine of theta times cosine of theta. And now, right, we can only cancel or reduce in a fraction when the numerator is factored, the denominator is factored. Then we can cancel out a common factor between the numerator and the denominator. And so let's factor out that numerator, noticing that there's a common factor of 2. And so now the numerator is factored, the denominator is factored. I see that common factor of 1 plus sine of theta that I can cancel out, and I have 2 over cosine of theta. And well, 1 over cosine of theta is secant of theta. And so this is 2 sets of that. This is 2 secant of theta. Right, maybe I'll write it down here that 2 over cosine of theta, this is the same as 2 times 1 over cosine of theta. And we know that 1 over cosine of theta, that's the reciprocal of cosine of theta. That's the trigonometric function, the reciprocal trig function, secant of theta. Okay, so that was a little bit more work than the first example, but hopefully that showcases to you one approach when it comes to simplifying trigonometric expressions is just performing the operations at hand. Here we just added the two fractions together, but then we also noticed that we could use the Pythagorean identity here when we saw that sine squared of theta plus cosine squared of theta. So almost as frequently as you'll use this Pythagorean identity, sine squared of theta plus cosine squared of theta is the same as 1. Oftentimes you'll need to use variations of this identity. And there's actually many variations. I'm only going to cover 2 right now, and these might feel obvious, but I just want to take a moment to emphasize them. So if this expression is true, or if this equation is always true, regardless of theta, well then it's always true also. Let's say if I subtracted sine squared of theta from both sides, I would get that the statement 1 minus sine squared, maybe I'll write it this way. If I subtracted sine squared of theta from both sides, I would get cosine squared of theta is equal to 1 minus sine squared of theta. So this is another statement that's always true. But we could have done it the other way around. We could have subtracted cosine of theta from both sides of that original equation, and it could have ended up with sine squared of theta is equal to 1 minus cosine squared of theta. So these are variations of the Pythagorean identity. And what I want to point out is that if you see something like this, if you see 1 take away sine squared of theta, or if you see 1 take away cosine squared of theta, you know it's the square of the other trigonometric function. So this is just a variation of the Pythagorean identity. So let's go ahead and try this example here. So in this example, we're going to have to use that idea. And if you're feeling up for it as well, please go ahead and try this problem out first. So usually, if you're dealing with a trigonometric expression involving some of our reciprocal functions, it can be pretty beneficial for us to write everything in terms of sine and cosine. Right, so this expression can be rewritten as, well, secant is the reciprocal function to our cosine function, so it's 1 over cosine of theta. Then we have minus cosine of theta. Maybe because I see a fraction here, yeah, I'll write it as cosine of theta over 1, right? Cosine of theta, that's really the same thing as cosine of theta over 1. Maybe later we can try and subtract these two fractions. But then we still have this sine of theta in the denominator. Right, so there's this sort of bigger fraction at play here. And so maybe let me just focus on the numerator for now. The numerator of the main fraction here. Now let's try and subtract these two fractions, and to do that we need a common denominator. So I'm going to go ahead and multiply this fraction here by cosine of theta over cosine of theta, right? That would give us the common denominator of cosine of theta and allow me to subtract the fractions, right? This becomes 1 over cosine of theta. Take away cosine squared of theta, right? Cosine of theta times cosine of theta is cosine squared of theta, all divided by sine of theta. So continuing with this main numerator, we can now subtract the numerators of those two fractions there. Right, they have a common denominator. We have 1 minus cosine squared of theta over cosine of theta. And then we have the main denominator, sine of theta. And so this is where we can use that idea, right? 1 minus cosine squared of theta, this is the same as sine squared of theta, right? If I start with the Pythagorean identity, sine squared of theta plus cosine squared of theta is equal to 1. Subtracting both sides by cosine squared of theta gives me sine squared of theta is equal to 1 minus cosine squared of theta. And that's really what we see here. That's the same as sine squared of theta. Maybe I'll use purple here just to emphasize that that's where we're doing this swap, this relationship here. Okay, and then now, right, we have this division of fractions. I can think of this division here, this main division, as sine squared of theta over cosine of theta. This is being divided by sine of theta. In other words, it's being multiplied by the reciprocal of sine of theta. Right? This is sine squared of theta over cosine of theta. So this part here says multiply by 1 over sine of theta. So this comes out to be sine squared of theta over sine of theta times cosine of theta. And so, right, this numerator is telling me sine of theta times sine of theta. This denominator says divide by sine of theta. Right, there's that common factor of sine of theta, and so we can cancel out one of them and end up with sine of theta over cosine of theta. Right, maybe just to really write that out. Right? This is the same as sine of theta times sine of theta divided by sine of theta times cosine of theta. And so we can cancel out one of those factors of sine and end up with just sine of theta over cosine of theta, which is the same as what we call tangent of theta. Okay, so that's one way of simplifying that expression, that original trigonometric expression. And something I'd like to mention is that there's typically multiple paths to simplifying a trigonometric expression. This is just one of them, and probably the one that I find the clearest. So another kind of problem you'll encounter is one phrased as verify the identity. Usually they'll give you an equation, a left expression and a right expression, and ask you to show how you can simplify one expression into the other. So, for example, the previous problem that we did, it can be restated as verify the identity that secant of theta minus cosine of theta all divided by sine of theta is equal to tangent of theta. So really they kind of give you the two expressions. They want you to sort of start with one and see if you can manipulate it into the other. And so really, if I were to give you a problem like this to verify this identity, all the steps from the previous problem would really be the answer to this kind of problem. Right, so all of the work that we did in this previous problem here, these are steps you would need to show to verify the identity that really this expression here is equivalent to this expression here. And so let's go ahead and do an example. So here I want to verify this identity, and again, we're just trying to show that these two expressions are equivalent, that I can simplify one into the other. And usually it's easier to start with a more complicated expression and simplify it or manipulate it into a simpler one. It's harder to do the reverse. And so let me make the recommendation that typically for these problems you want to start with the complicated side. And manipulate it into the simpler side, the simpler expression. And then the other thing I really want to point out is that, okay, there is an equality sign there, but this is not equivalent to the problem of solving an equation. This is not asking us to solve the equation above. We're not going to perform the same operations to both sides of the equation. We're really just going to take one expression and simplify it into the other. And so in this expression, I would say that the right-hand side seems to be the more complicated one. So maybe let's start there and see if we can just work with it a little bit and arrive at the other expression, 2 tangent of theta times secant of theta. So let me rewrite it down here. So 1 over 1 minus sine of theta, take away 1 over 1 plus sine of theta. So these are two fractions that I'm asked to subtract. So let's go ahead and perform that operation. Let's subtract them. And to subtract them, we need to make a common denominator. So I'm going to multiply this first fraction by 1 plus sine of theta over 1 plus sine of theta. Right, this is just 1. And then I'm going to multiply the second fraction by 1 minus sine of theta over 1 minus sine of theta, so that we have that common denominator of 1 plus sine of theta times 1 minus sine of theta for both of these fractions. And so here in this first fraction, right, multiplying 1 plus sine of theta to the numerator, 1 gives us just 1 plus sine of theta. And then this denominator, it might not be so apparent at first, but let me go ahead and rewrite this down here so that it's clear what this is equivalent to. So if we multiply 1 plus sine of theta and 1 minus sine of theta, well, what we have here is a difference of squares, right? If we have 1 times 1 and 1 times minus sine of theta, and 1 times sine of theta, and then lastly sine of theta times minus sine of theta gives us minus sine squared of theta, we get this cancellation here. So we just have 1 minus sine squared of theta is the result from this product, right? This difference of squares. So this is 1 minus sine squared of theta. And again, there's nothing we really want to cancel out here. We did this multiplication of 1 plus sine of theta over 1 plus sine of theta so that we can end up with this common denominator. Right, so here, 1 plus sine of theta times 1 minus sine of theta, this gives us the same denominator. That was the point of doing this. And now we can actually subtract these two fractions. And how do we do that? Well, we just subtract their numerators, right? So I have 1 plus sine of theta. And I'm going to subtract away the numerator. And really this means subtract away the whole numerator, not just that first term, but the whole numerator of the second fraction. Right, again, our goal at the end of the day is to end up with this expression 2 times tangent of theta times secant of theta. And it's not clear that we're going to end up there so far, but really this is the most apparent approach I can think of, is just to put these two fractions together and just, sometimes we just need to run with it and see if anything sort of falls out. So subtracting away that numerator gives us 1 plus sine of theta. We have minus 1, and then minus negative sine of theta gives us plus sine of theta. So we get this cancellation here, right? 1 and minus 1, but then we have sine of theta plus sine of theta, right? This is 2 sine of theta in the numerator over 1 minus sine squared of theta. And this is where we can use that identity again, right? 1 minus sine squared of theta, what is that equal to? That's equal to cosine of theta. Right? If I have sine squared of theta plus cosine squared of theta is equal to 1, if I subtract away sine squared of theta from both sides, I get cosine squared of theta is equal to 1 minus sine squared of theta. And that's exactly what we have here, 1 minus sine squared of theta. And what we're saying is that that's the same as cosine squared of theta. So we've got 2 sine of theta over cosine squared of theta. And we wanted to show that our expression was the same as 2 times tangent of theta times secant of theta. Well, I can sort of break this fraction apart. This is the same as 2 times sine of theta over, how should I write this? Maybe I'll write it this way, cosine of theta times cosine of theta. I can break this even further apart as 2 times sine of theta over cosine of theta times 1 over cosine of theta. So this might be a little bit more work than is necessary, but I just want to make it very clear, very apparent what's happening. And then this ends up as 2 times, well, sine of theta over cosine of theta, that's the same as tangent of theta. And 1 over cosine of theta, well, that's the reciprocal function, secant of theta. So this is exactly what we wanted to show. We wanted to show that these two expressions were equivalent. And so we started with this. And we didn't add anything new into this problem. We didn't change anything about this expression. We just sort of manipulated it, performed the operations, maybe multiplied by 1 in a little bit of a funny way. And we also use the Pythagorean identity, but that's the statement that's always true. So here we used those ideas to take this expression and turn it into that expression.